Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into the fascinating world of multiple processor scheduling. Sheila, are you ready to explore this complex topic?
Absolutely, Victor. Multiple processor scheduling is a crucial aspect of modern computing systems. As we've seen in previous episodes, CPU scheduling is already complex with a single processor. Now, imagine the challenges when we have multiple processors working together.
You're right, Sheila. Let's start with the basics. In multiple processor systems, we have two main types, homogeneous and heterogeneous. Can you explain the difference?
Of course, in homogeneous multiprocessing, all processors are identical and can perform the same tasks. This is common in many modern computers. Heterogeneous multiprocessing, on the other hand, involves processors with different capabilities or architectures. A great example of this is your smartphone, which might have a mix of high-performance and energy-efficient cores.
That's a great explanation, Sheila. Now, one of the key challenges in multiple processor scheduling is load balancing. Can you elaborate on what that means?
Certainly. Load balancing is the process of distributing the workload evenly across all available processors. The goal is to maximize system efficiency and minimize idle time. It's like a chef in a busy kitchen, making sure all cooks are working on different dishes simultaneously to get meals out quickly.
Excellent analogy. However, there's a concept that sometimes conflicts with load balancing: processor affinity. Can you explain what that is and why it's important?
Processor affinity, also known as CPU pinning, is the practice of assigning a specific task or process to a particular processor or set of processors. While it might seem counterintuitive to load balancing, it can actually improve performance in certain scenarios. This is because when a process runs on the same processor, it can take advantage of data already in that processor's cache, reducing memory access times.
That's a great point, Sheila. It's all about finding the right balance between load distribution and efficient resource utilization. Now let's talk about a more advanced concept: NUMA systems. What are they, and how do they affect scheduling?
NUMA stands for non-uniform memory access. In NUMA systems, memory access time depends on the memory location relative to the processor. Some memory areas are closer to certain processors, meaning faster access times. This adds another layer of complexity to scheduling, as the system needs to consider not just processor availability, but also memory proximity for optimal performance.
Excellent explanation, Sheila. Now let's bring this discussion into the modern era. How has the rise of multi-core processors impacted multiple processor scheduling?
Multi-core processors have really changed the game, Victor. Instead of having multiple separate processors, we now have multiple processing cores on a single chip. This brings benefits like shared cache and faster communication between cores. However, it also introduces new challenges, such as managing shared resources and avoiding contention between cores.
Absolutely right, Sheila. And it's worth noting that many of the principles we've discussed apply to both traditional multiprocessor systems and modern multi-core processors. Now, let's talk about some real-world applications. Where might we see these multiple processor scheduling techniques in action?
Great question. We see these techniques in action all around us. High-performance servers in data centers use sophisticated scheduling to handle thousands of simultaneous requests. Gaming consoles like the PlayStation 5 or Xbox Series X use multiple cores to handle complex graphics, physics simulations, and AI simultaneously. Even our smartphones use heterogeneous multiprocessing to balance performance and battery life.
Those are fantastic examples, Sheila. As we wrap up, what would you say are the main challenges that operating system designers face when implementing multiple processor scheduling?
The main challenges revolve around complexity and trade-offs, Victor. Designers need to balance load distribution with processor affinity, manage shared resources effectively, and optimize for different types of workloads. They also need to consider energy efficiency, especially in mobile devices. It's a constant juggling act between performance, efficiency, and fairness.
Well said, Sheila. To recap, we've covered homogeneous and heterogeneous multiprocessing, load balancing, processor affinity, NUMA systems, and the impact of multi-core processors. We've seen how these concepts apply to real-world systems, from servers to smartphones, and discussed the challenges involved in implementing effective multiple processor scheduling.
Exactly, Victor. It's a complex topic, but understanding these concepts is crucial for anyone working with modern operating systems or high-performance computing.
Absolutely, Sheila. And that brings us to the end of today's episode. Thanks to all our listeners for tuning in to Operating Systems Crashcast. Until next time, keep your processors balanced and your scheduling optimized.